This particular topic is actually considered by some people in statistics to be the most important thing in statistics. When we are dealing with our data-driven decisions, many times the question that we are asking is, what values can I expect from a population based on the sample? So the process of doing statistics and knowing what to expect, a lot of times we don't have the actual population numbers to go by. And so we're going to be using sample numbers. That's called the process of statistics, right? Using the sample to get information about the population. And that is what the confidence interval is designed to do. So you need to know this. The confidence interval is used to give measurement for a population. When I use a confidence interval, the result that I'm going to have is not about samples. When I use a confidence interval, the result that I have is about the population. I don't actually know this measurement from the population, but based on the confidence intervals, I have a level of confidence that it's between two numbers. And if you think about how that would work, we talked about this a little bit last time. If I'm going to eat lunch, and I'm actually going to ask the question, how much money should I bring in order to be able to have enough to have my lunch? And we're going out to eat. If we say, well, lunch can cost anywhere from $0 to $100. Well, that's true, but it's not helpful because it really doesn't give me an idea that I want to be able to use. It's not what they call actionable. It's not practical. But if someone says to me, well, your lunch is going to cost somewhere between $5 and $5.10. Well, that would be great if they knew what they were talking about, but the fact is they don't. You can't be that precise about the process. You can't know that that's true. So that might be really helpful, except it's not true. So what do you want? You want things that are true, and you want things that are helpful so that you have a range of possibilities that will allow you to make a decision. But it's not so broad that it's not helpful, and it's not so narrow that it runs a risk of being wrong. So then how do we balance that? How do we make that happen? That's the idea of the confidence interval. That's what confidence intervals are designed to do. And we're going to be seeing this a lot. We're going to be seeing this constantly. And then we'll talk later about how different kinds of things are kind of different. So you'll be famous now. if you have a situation where you say, I'm going to know how much confidence to have. We have to have some mathematical way of making that happen. So we're going to use a few different symbols. The first symbol that you need to understand is alpha. It's a Greek letter. It's kind of like an A, but it's a little bit curved or whatever. And what does alpha stand for? Alpha is the chance of being wrong. And so we want to actually make alpha to be a relatively small number. Specifically, we choose traditionally 3 different values for alpha. So we would have alpha to be 0.01, 0.05, 0.10. Those are the standard values for alpha. Because we want to have a relatively low chance of being wrong. Seems reasonable. And of course, the most popular is 0.05. That's how we want to make it unusual for us to be wrong. Now, certainly, if you think about how this works, let's just say that you're walking across a crosswalk and there's a car coming. And there's ice all over everything. And you say to yourself, okay, I'm going to run a risk here. If I step out in front of this car, will they be able to stop in time? So you have to run a risk. But then you have to be smart about that, right? You're actually looking around and saying, this is completely glare ice. There's no way this car is going to stop. But I'm just going to walk in front of it anyway. That doesn't make a lot of sense, okay? But if it's a relatively dry pavement and you've got relatively good footing and you're making your way across and there's a big stoplight right there and you're supposed to be in the crosswalk and you are, all that stuff's together, you're not going to say, oh, well, I have to wait for the car to go by. That's not going to work because the light's red. The car's not going to go by. So you just keep walking and the car stops and everybody's okay. But you have to make that choice. You have to consider the probabilities and the possibilities of what's going to happen. So you would not want to go out and say, I'm going to take a big risk. You don't want to have like a 20% chance of being wrong. But you're not going to sit there and say, I have to wait until every possible thing can be exact, or I'm not going to even move. By the way, this is one thing about self-driving cars, right? Self-driving cars have a lot of trouble at 4-way stops. Why is that? Because they don't want to have an accident. Well, this car is moving over here, so I'm going to wait until it stops moving. It stops. Well, can I go now? Well, whose turn is it? How can a self-driving car figure out how polite it's supposed to be? It doesn't know how to do that, okay? So it comes up there and it's moving forward, and then, oh, somebody moved over somewhere. I better stop. And you're sitting in the middle of the intersection. Oh, hi, everybody. I'm a self-driving car. That just doesn't work very well. So you've got to be able to take some chances and be able to feel the possibilities of what might happen here, and then sometimes you just go. Everybody's like, oh, what an idiot. But hey, they went, and now we can still go on with our lives. But it's not just a matter of saying, what is the number for the chance? You have to think about what's going on in the situation. What is the practical significance of the thing? So these are guidelines, and then you have to actually think about what's important when you pick these numbers, okay? So alpha is being the chance, or the chance of being wrong. And so then we talk about the level of confidence. How confident are you about something? So then your level of confidence, if this is being wrong, 0.01, then this would be a 99% confidence, 95%, and 90%. So you want 95% confidence. You can maybe deal with 90% or 99. but 95 is the most common. And by the way, if I don't say to you, we're using alpha of 0.01 or 0.10, then you say to me, I'm going to use an alpha of 0.05. Okay? So right now, alpha is 0.05 until somebody says otherwise. Question?
Why isn't the confidence interval not just 2 standard deviations on both sides?
I will get to that in just a minute. Okay. So then when we say, all right, how do I want to make this work? I want to be able to have an interval that works most of the time. And if you go to your textbook and you look at page 429, you will see what we're talking about here. And hopefully you've got your electronic version, you can make that happen. Because this is a relatively important picture here. Oh, it's not 429, it's a different page. Ah, I hate it when that happens. Okay. Chapter 9. There it is, page 424. So page 424 is the graphic image that shows us what's happening here. I'm just going to throw it on the video. Look at that. See that? That's the thing right there. Okay. So what's happening here is that you see there's a ton of different intervals where we try to estimate the actual population number. And so it's like what I was doing last time, trying to hit a target with a relatively large weapon. Okay? If you have a big thing and you're trying to hit something, you're most likely going to hit it. But sometimes you won't, because it'll be too far to one way or the other. So we have a certain specific value, and we're using intervals to try to hit that. Many of the intervals will, but some of them will not. So when we ask the question, what does the confidence interval do really? It's trying to hit a target, but it doesn't hit it all the time. So if I'm out here and I have this as my confidence interval, and I say, I think the population number is somewhere between this left side and this right side, I could be wrong. And in fact, this out here at the very far end of this, it's pretty much impossible that it could be out there. And it would be more likely the more I get towards the middle, but I don't know where the middle is. So I don't know if the middle is in my interval, or if it's on the left side of my interval, or if it's outside my interval. I just don't even know. But that's the best we can do. We're going to try to hit the target. And we're going to try to hit the target with enough of an interval that we're going to have a certain amount of chance that it's going to make it work. Now, like I've said before, people have done this for a long time, for many years, and it pretty much gives us good results, and so we just keep going with it. But we have to make certain assumptions. And when we make those assumptions, sometimes they're decent, sometimes they're not, but most of the time we're okay. So when you say, well, what are the exact mathematical foundations of this? It's like, well, if we assume this, and this, and this, and this, and this, and that, it works. Well, what if one of those things doesn't work? Well, maybe it's not important. We're not sure. Do it anyway. Okay, and it works. Okay, we're good. And that's kind of what happens. So we want to try to do the right thing and the good thing, but sometimes we just say, well, it's good enough, and that's all right. Now, what you just said about the 2 standard deviations. The first thing is we're going to be a bit more exact now, instead of saying it's just 2 standard deviations from me. Because what we're going to say is we're going to use a bell-shaped situation, which we already talked about. And specifically, when we have this bell-shaped curve, we're going to take two tails like this. Because in a confidence interval, there's a possibility of being wrong either on the left or on the right. So we're going to take this, and we're going to have this area be alpha divided by 2. So when we think about what's our chance of being wrong, we're going to say that's alpha, and then that's going to help us to know where our interval is. So we're going to take alpha divided by 2, so it can be either way, one or the other. So that can be helpful, but what exactly is that number? Well, I need to find out from my z-scores what that number is going to be. Well, if I look up 0.025 on this side over here, that would be 2.5% over on the left-hand side. What z-score corresponds to that? If you have your z-scores handy, or you can look them up, what do you see when you say 0.025? 1.96, and this happens to be negative on this side. And this is 1.96 on the other side. So we're going to be a little bit more exact, so it's no longer just 2 standard deviations. It's a z-score of 1.96 on one side or the other. Now that's not a huge difference, but it's something. And then once we establish that, then we can change our alpha to be something else, and then we can figure out what those values are going to be. As it turns out, these are called critical values. So if I have a 95% confidence interval, my critical values will be 1.96. And, plus or minus to the right or to the left, 1.96. And then we have other ones for a 99% and for a 90%. And these are given to us in our textbook. It's on page 425. This is 1.645, and this is 2.575. Once we have these, then we don't have to go through the process of looking up z-scores. So that's pretty nice. Now, once we have the concept of the interval, then, when you think about how this works, you think about having the mean and then this many standard deviations either direction of that, okay? And so then you get a formula which is actually given to us in the textbook on page 426. But what we have to do here, since we don't know the population number for the proportion, we're going to use the sample proportion, and we're going to hope that it's close enough that it's not making that much of a difference. And as it turns out, most of the time we're okay. So then what we end up with is a confidence interval for the population proportion. And what we have are numbers on either side of that. This one is p hat minus z of alpha over 2 times the square root of p hat times 1 minus p hat over n. And then over on this other side, It looks the same, but it has a plus sign. So mathematically, hopefully you can see how this works. You have a value, and you're going to go z times the standard deviation above, and z times the standard deviation below, and that will be your interval. But like I said, we don't know what p is, so we just throw p hat in there, and it works most of the time. So this is then the confidence interval for the proportion. Now, again, we have conditions on this, okay? So that we have to say things like, we have to have that thing n times p hat times 1 minus p hat is greater than 10 to make it bell-shaped. And we also want to have it be so that it's not what we're doing here, since it's a sample, it has to be a certain size smaller than the entire population. But those are relatively minor conditions, and we usually don't worry about them as long as our sample size is relatively large. Like I said previously, if we have something like 800 or 400 or 700 in our sample, then we're probably okay. Once you get down to like 30 and 15, then we would have to have different techniques, which are out there, that we could use for this. Now, when we say, what does this thing actually have in it here, then this equation could be rewritten this way. Where the complicated thing right here is considered to be the margin of error. So this letter E is the margin of error. And so then we would have something like 28% plus or minus 4.5%. So this is the margin of error, plus or minus 4.5%. If that was the situation. This is very common. This is like when CNN does a survey, they say these results are accurate within 4 percentage points. That's what they mean, plus or minus 4%. If you really want to know, this thing, which is in the square root here, it's the standard deviation of the sampling distribution, right? We said that. This is called the standard error. And you might see that if you're using software, you'll see things that refer to the standard error. That's what that is. All right. So having this in mind, let's pick an example. So let's say that I've got something like healthcare, right? And I say, I want to know, for example, in this area, how many people visit the emergency room in a 2-year period. Okay? So my question is, how many people visit the ER within 2 years? And I'm looking for a percent. How many, what percent? So I go there and ask a bunch of people. And let's just say n is equal to 500. And I get a number back, let's say 300 say yes. Well, then when I consider that to be a success, they say that this happened to them, then I would say that's X. X is equal to 300. It's might be a little bit high. Okay. 300 people out of a 2-year period? Well, let's just say it's a certain, whatever, like a certain company, and they do certain kinds of high-risk things. All right. So 300 of them say this. So when we say 300 as X, then P hat would be 300 divided by 500. So that's 0.6. So now we're going to do a 95% confidence interval. Now, if you have graphing calculator or other kinds of technology, you can just say, hey, I want a confidence interval. Just drop in the numbers. This is what I want. Boom, there it is, as they say. If, like me, you've constructed your own spreadsheet to make this happen, then that makes it nice. Let's see, I've got to get this right. So, confidence interval for the proportion. So I put in my sample size, which is 500. I put in my observed amount, which is 300. I get a p hat of 0.6. And since I'm doing a 95% confidence interval, I put in a 0.05 for alpha. And then if you want to actually use this formula, then you would put these numbers in. You'd have 0.6 times 0.4 divided by 500 square root multiplied by 1.6. That gives you your margin of error. Add it and subtract it to 0.6, and all that would happen. So then what you'd end up with is from 0.557 to 0.643. That would be your 95% confidence interval. I'm pretty sure you can also do this on StatCrunch. So you can just tell StatCrunch you want to do one of these and then say, oh, I've got this stuff and I want to make it happen, and we'll just make it happen, which is nice. So what does that really mean? What that really means is I did this survey of the people at this company, but I did not talk to everybody. I only talked to a sample. I only talked to 500 people. So the question is, what is the real population value? The answer is I don't know. But I'm 95% confident that it's between 56 and 64%, more or less. So that's what I can say. Now, how important are those limits? If you say it's between 56 and 64, is that a big deal? I don't think so. I mean, it's kind of 60-ish in there. So a lot of times when we get these numbers, they may not have a lot of practical value. Sometimes they do, though. In this situation, this is how much we are able to say within those limits of making confidence. Now, what if we said, I want a 99% confidence interval? Well, if I want a 99% confidence interval, I want to be more confident of my results. Change my alpha to be 0.01. I get from 54.4 to 65.6. would you say that that made a lot of difference? Going from 95% to 99%. Has it substantially changed our information? Not really. That's why 95% is usually what we do. It's like, you go to 99, it doesn't matter. You're pretty much sure that this is what's going to happen. So you say, yeah, this is what's going to happen between these numbers. However, let's just say that I wanted to get a lot more accurate than this. How could I make this come out so that I was really accurate in this situation? Well, if you look at the equation, you see that this margin of error depends on n on the bottom of this fraction. So if I make n large, that will make my margin of error small. So let's just say I go crazy here, and I'm not just going to have 500 people. I'm going to do 10,000 people. This is a nationwide company. It has a lot of employees. I'm going to ask 10,000 people, but I had the same result of 60%. Okay. So I had 3,000 people. No, 6,000. 6,000 out of the 10,000. And it's a 95% confidence interval. Well, it's between 59 and 61%. Wow. So I can get really accurate if I want to, but it's going to take me forever to do that, right? So what we've talked about before is I need to balance the amount of value I get from my information with how much value I got to put into it. How long would it take to interview 10,000 people as opposed to 500? That's craziness. So if you don't need it to be this accurate, then you're not going to ask that many people. You don't have to. So this is what's happening in this world of statistics. We are balancing the question between how much accuracy do we need and how hard is it to get that information. We might not need to ask that many people. So then, we actually have a formula that we can use for the sample size. Given a value of E. If I have this idea, how accurate do I need this to be, then I can find N, the sample size that I need in order to get that much accuracy. Now, certainly this would be relevant for something like a political campaign. I want to know if my candidate is going to win and by how much, okay? In fact, as it turns out, in political campaigns, how much the margin of victory determines how much money usually people put into the campaign. So let's just say you're a billionaire and you want to influence elections. You're not going to spend a lot of money on a person who's at 25 or 30% possibility, right? It's like, they're not going to win. Why would I try to give them a ton of money? But if you got somebody that's 47, 48%, they might win this election. Then you might put a few $1 million into their campaign to say, hey, I want this person to win, so I'm going to make this contribution. So then the close races become the place where people want to put their resources politically in order to make various differences. Well, of course, if it's the Russians, that's a problem, right? Yeah, say, okay, well, the Russians want to make this thing happen. They want Trump to get in. Well, that's not very good. But what if it's an American? Okay, if it's an American, maybe then it's okay. Certainly, if Trump wants to win and Trump pays a person to put ads on Facebook, then, well, who knows? I think that ship has already sailed a little bit. But all right, so anyway, the concept of saying the margin of error, how much of an error that I have, I can use that to make a sample size to be a certain amount. And there's a formula for that. Did you have a question, by the way, Zach? Okay. So, that formula, which unfortunately is hard for me to remember, and this is on page 430. And it looks like this. N is equal to p hat times 1 minus p hat multiplied by the critical value, which is the z-score, over capital E squared. So if we were to say, I want a certain amount of accuracy in my result. Let's just say I want to have a 2% amount of accuracy, plus or minus 2%. Well, if I want a 2% accuracy, then E would be 0.02. And then I have to decide what my confidence level would be. So 1.96. 1.96 here over 0.02. That's going to be squared. And then we have 0.6 multiplied by 0.4. So our question right now is, how many people do I need in my sample if I want to be accurate to within 2% for a 95% confidence interval, given that I have a previous number of 60% as a surveyed amount? So then I can make that happen. And once again, if you have a spreadsheet that's already set up, that's really nice. And then this comes out to be 2,305 people. Now, most textbooks and most textbook software say that you have to round this number up. No matter what you get, you round it up to the next whole number. And I'm like, you guys are just too crazy for your own good. 2,305 people versus 2,304 or 2,306, who cares? What's that one person going to do? It's not going to make or break anything here. These are just ballpark estimates in the first place. That 0.6, that was rounded off, okay? You don't know that that's true. And so your error is 0.199 instead of 0.02. That doesn't matter. So this is all ballpark estimating, okay? 2,300 people more or less would give you this amount of accuracy more or less, but it's not exact. But they insist and they say, if you get a number, you're supposed to round it up to the next whole number. And I'm like, okay, fine. But it means nothing really. It's just a ballpark number to say, you should probably have somewhere around this number to get this more or less amount of accuracy up. Okay, good. That's fine. So that works. So the process here, though, when you say, does this give me what I want? It's giving me a real good idea of where the population number is, but I didn't have to talk to everybody. I only talked to 500 people. I get a decent idea of what the actual result is for everyone in the population. And if I'm randomly picking from people in the United States, you know, there's like a few 100 million people in the United States, but I'm only talking to 500 of them. But if I'm randomly generating these lists of people, then I'm still pretty much accurate within, 5% one way or the other. So it's getting me good information without having to talk to the entire population, assuming that these things are randomly selected. and assuming there's not some confounding variable out there that's making stuff weird. So this is all pretty good. All right, so I'm going to